Hello, my name is Brian Sumali. I'm a senior assistant professor of Keio Global Research Institute, and today I'm going to explain about myself and my research. First of all, my background. I'm an Indonesian. I obtained my Bachelor of Science in Information Technology from Indonesia with my thesis related to the AI field. I pursued my master's degree in Malaysia, focusing on image processing. Then, I obtained my PhD from Keio University under the guidance of Professor Mitskura with the research focusing on psychiatric disorder screening. The commonality between all of these are data analysis and signal processing. Right now, I'm very interested in digital biomarkers. So now, to quote from WHO mental disorder key facts, 1 in every 8 people in the world live with a mental disorder, of which anxiety and depressive disorders are the most common. Normally, a comprehensive assessment takes at least 30 minutes to complete, and that's only for one patient. If we add the commuting time to the hospital, and we also compute the paid day off that is required to visit for the hospital, it's very obvious why a faster and simpler assessment is needed. Now, on the other hand, we also now live in a society with quite advanced technology. Many of the conventional devices now record our biosignals. If we are somehow able to utilize this data and we are able to process them to screen mental disorders, then surely this will be very beneficial for our society. My researches are related to the aforementioned objective. 2 of them are now publicly available for anyone that's interested. Now, first of all, I would like to explain about my research for screening depression just based on a person's facial features. In this experiment, the participants did a free talk session for around 10 minutes. One might be able to imagine that a healthy person might do the session with a light mood, while the depressed person will seem more gloomy or darker in general. This mood are reflected in the changes or the activity of these facial landmarks, and we exploited those features to both, 1, develop an accurate machine learning model for screening depression, which also predicts the severity, and 2, infer which features are important. So human doctors might be able to use those features to aid as an aid of their screening as well. Next is about dementia and mild cognitive impairments, or MCI. Although the following is true in most of the developed countries, the aging society problem is especially severe in Japan. Shown in the left histogram is the population estimate by age. In this year, the median age is now around 50s. In addition to the aging society problem, official sources from Japanese government estimate that in Japan, year 2025, 1 out of 5 people older than 65 years old will have dementia. This makes the early prediction of dementia or MCI detection a very, very important task. Just last year, our research group led by Professor Mitskura found the possibility of using frontotemporal EEG for detecting MCI. MCI is said to be the prelude of dementia, and detecting MCI before any symptoms appear is very crucial. Our main findings for this research is that there is statistically significant difference in EEG power between the dementia groups, MCI groups, and healthy groups when we compare the delta and low alpha bands. Finally, this is my ongoing research about sleep disorder and cognition. Before proposing an experiment, it is imperative to test the possibility and methodology first. In this case, we decided to use a data set available from National Sleep Research Resource or NSRR. which is MROS sleep study, osteoporotic fractures in men. These are the details of the SAID database. The dataset was obtained from males 65 years old and plus. The data was obtained by using polysomnography or PSG, and both EEG and ECG are available. The original objective of this data sets is not for cognition, but since they are also including the Tanks modified mini mental state exam for 3MSE as a measure of cognition, we think that it's suitable enough to test our possibility, our hypothesis. Now, the dataset that I'm using only uses the first sleep visitation only. The sample size is 414, and 3 channels from PSG are utilized: the EEG, 2 channels of EEG, and one channel of ECG. These are then further processed. The EEG is converted to power spectra by using fast Fourier transform, while the heart rate variability is first detected from ECG, and then we measure the HRV features by using AR model. After feature extraction, we filter those features using lasso, such that only important features remain. The objective was to predict the 3MS values. One major limitation is that technically all of the data points are from healthy subjects. So we are not expecting a very significant result, but just a small correlation will do it. And this is our findings from the datasets and the methodology. After we used lasso to reduce the number of features, the remaining features are EEG power for alpha and gamma bands, the EEG fluctuation for beta and gamma bands, and the LF-HF ratio, low frequency to high frequency ratio. This is an HRV feature. The main finding is that the R-squared correlation is 0.32, which indicates a moderate correlation between the features and the 3MSE. This is more than what we expected. To conclude, we found moderate correlation between the EEG, ECG features with 3MSE. Additionally, as the LF-HF feature might also be computed using only heart rate, it opens the only possibility, of predicting cognition using simple heart rate measurement devices. However, we must remember that these results are based on healthy volunteers and might not be generalizable to the MCI and dementia patients. Future work should address these points. Finally, this is another step for developing easy biomarkers for measuring cognitive health. Thank you very much for your kind attention.